Okay, this is the 6-1 notes for Precalculus 2. In this section, and the next one, we're going to be talking about trigonometry as it relates to non-right triangles. We specifically call non-right triangles oblique triangles. Okay, the two triangles you see below are both examples of oblique triangles. This is called an acute oblique triangle. This is called an obtuse oblique triangle. What they're called is not important, but there are the two types that you actually would run into. So among oblique triangles, there's this interesting relationship called the law of sines, and the law of sines is actually written right here. So the law of sines, at first students are sort of thrown by it because there's actually two equal signs in it. So why are there two equal signs? Because this is more about taking two of these ratios at a time. So the first ratio is a over sine a. So what does that mean? So look up here. So you have a side a, and then that's over the sine of the angle that is opposite it. What they're saying is if you take that ratio, it will be the same as taking side b over the sine of the angle opposite it in our problem. So we only have to take two pieces at a time of this. So this equation essentially is creating three different equations. We either take this one, a over sine a equals b over sine b. We take a over sine a is equal to c over sine c. Or we can take b over sine b is equal to c over sine c. Any one of these sets of ratios is perfectly fine for setting up this equation. Now, the key is in using these equations is if you look at it, this actually has four variables. We have little a, little b, big A, and big B. So the key to this formula is if you can get three of those variables have values, then that means you should be able to solve for the remaining variable that's in the problem. That is the whole focus of the law of sines. Okay, before we go to use it, let me do a little bit of a proof to prove why this actually works. So let's say we take looks like an acute oblique triangle, and we drop an altitude down the middle here. Remember, an altitude is a right drawn to the right angle of the opposite side, that back from geometry. So what we're going to do is we're going to find some trig relations inside of this. Now, why can we do that? Because we actually have three triangles here, the big one, but we also have a small triangle here and a medium triangle here on the left and the right. We're going to use those triangles in order to find what the missing pieces are here. So over here, sine A. So what is the sine of A? Well, we're right here. The sine of A in this little triangle is going to be opposite it, which is little h, over hypotenuse, which is b, so h over b. If you go to b, which is over here, if we go opposite it, we have, again, little h, but this time over big A. Okay, so interestingly enough, what that creates is a scenario that we can actually move forward with and form an equation. Why? Because if you look at this, both of these have h in them. So if we can solve for that h in both equations, we should be able to do something algebraically. So let's say we took this first equation and we multiply both sides by b, so we solve for h. We're going to get b sine a equals h. What about the other equation over here? If we multiply both sides by a, we get a sine b is equal to h. Therefore, if we know that b sine a is equal to h, we should be able to put it in for h in the other equation. So let's do that. So we're going to get a sine b is equal to b sine a. In the same step, we can basically divide both sides by the sine equation. So we're going to divide sine A this way to the left and get A over sine A. And we're going to divide sine B the other way to get B over sine B. And we're going to end up with this equation, which is the first part of the law of sines. Note, if you have trouble with this algebraic step, just look at the last step and cross multiply to see that they are the same thing. So if we do that, we basically prove the procedures and how they work for our specific problem. So it looks like there was a little bit of a spacing issue here. So just note that in your notes, this is supposed to go to the following page, but worth noting. So if you see that, you're not confused. Okay, so the next important step is understanding when to use the law of sines, or in other words, what scenario you provided with where the law of sines can actually be utilized to find missing pieces of an oblique triangle. The key is understanding that whenever you're given two angles in your triangles and any one side, you are basically able to use the law of sines. Now, if you remember from geometry, we had little side angle abbreviations like you see over here, ASA, SAA. They were provided when you were doing congruent triangles. Well, we use the same types of abbreviations whenever we're dealing with triangles that are oblique, and we need to determine if we're going to use the law of sines or not. So if what they're saying is any triangle that fits this pattern will allow you to use the law of sines. So I'm just going to give you sort of a small example here. So if you have, what is ASA exactly? So if you have a triangle, looks like this, and you are provided with two angles in the triangle as measures. So let's just, actually let me put some actual angles in there. So let's say this was 80 and this was 60. If you're also given the side that is between the two angles, so for example, let's say this was 5. If you have a set of sides and angles in that pattern, then the law of sines will be able to be used in the problem in order to find missing pieces. That's the first part. What's the other one? The other one is SAA. So let's say you were given, again, a triangle. Let's do the same angles here, 80 and 60. If you're given two angles, but then you're given a side not between them, so it could be either 12 on this side, or technically it could have been on this side, then you again can use the law of sines in order to find the picture. So before you can do any problem, you must identify what the pattern is of the triangle and then determine. So in the next section, FYI, you're going to be using something called the law of cosines. I know, shocker, right? The law of cosines, and the law of cosines is going to have their own patterns. So on an exam situation, you're going to have to actually look at a scenario and go, which one can I use and which one can't I use? The key is that these patterns here, ASA, SAA, are going to be the patterns that are going to allow you to use the law of sines. Okay, so let's look at our first problem, number 1 here. It says, find the remaining angles inside in the triangle below. Recall that this is referred to as solving the triangle. Remember to verify which pattern of angle sides is provided before applying the law of sines. Okay, so what would you do in an exam? You would look at the triangle and you would identify it as not right, or in other words, oblique. Therefore, you cannot do something like 82 is equal to C over something else. You can't do that because it's not a right triangle. So all those rules you learned before are out the window. So instead, you identify it as oblique and immediately say, what is the pattern in this oblique triangle? So look at what you're given. You're given two angles, 82 and 64, and you're given the side on the bottom. So the question is that side between the angles or outside of the angles? Hopefully you realize that it's outside of the angles, therefore the pattern is SAA. So you can even see in the pattern that the S is not between the A's. So the other pattern is ASA over here. So you can see the S is between them. The S is not between them, so that is the pattern. Once you know that the pattern is SAA, you can now use the law of sines and be able to get your result. So how do you do that? So if you look at the problem, you can clearly see that there is only one pair of angle and opposite side that is provided. So immediately, if you look at the picture, you go, okay, look at A. They give you big angle A, which is 64, but little a, which is right here, is not given. So that's not it. If you go to B, you go, okay, they do not give me angle B, even though I could find it by subtracting the sum of the other angles by 180. But if you look over at B, they don't give you that either, so what's the point of that? There is no point. But the last piece, if you look at 82, right at the top here of this triangle, they do give you the side opposite, which means that the key variable in this problem in the beginning is C. Why? Because the ratio is going to be 14. Actually, let me write it out for you. 1 second. Okay, the key ratio is going to be C over sine of big C, right? So that is going to be 14 over the sine of 82. Okay, so this is going to be our key ratio that we're going to be dealing with in our problem. So what do? We set this ratio equal to one of the other ratios in the law of sines. But in that law of sines, we're going to have to find some other pieces. So if you look at this problem, remember, we had nothing for any of the b's. So what do? We basically look at the a's and go, well, we were given that a was 64, uppercase A. So we go, all right, well, we should be able to say that that's equal to little a over the sine of 64. Note, what did I say when we went through the original formulas up here? The goal is going to be to get 3 of the 4 missing pieces and find the missing one. So if you look right here, we have 1, 2, 3 of the angles, or 3 of the missing pieces, one side, and we can find the missing variable here using simple algebra. So how do we do that? Well, how do you solve a proportion, which is what this is called right here, is a proportion. How do we solve that? We cross multiply. Okay, so if we cross multiply, we're going to get over here, a times the sine of 82 is equal to 14 times the sine of 64. Okay, and what do we need to solve for a? So we can divide both sides by the sine of 82. Okay, the rest of this is calculator work. So you would type 14 times the 64, sine of 64 over the sine of 82, making sure you're in degree mode. And you would get approximately 12.7 as the missing side for A. 12.7. Okay, so a small thing you always want to check for. It is well known from geometry that the way triangles work is that if you have a bigger angle, then a side opposite is always going to be larger than the side opposite a smaller angle. So if you look at 82 right here, the side opposite it is 14. So then if you look at 64, the side opposite it is smaller, 12.7. So right now we're good. Why do I say that? Because what if you got an answer like 17.2 instead of 12.7? Then that would not make any sense. That would be an illegal triangle. You can't have a bigger side opposite a smaller angle. It just doesn't work. So that's just something to look out for when you check your work. So our first missing piece is 12.7. What else can we do? Well, we can find angle B by doing 180 minus the sum of 82 and 64. That's going to be 34 degrees. Okay, so that's one of the missing angles. Therefore, we can then move on and do the last ratio. So my suggestion is you try to use this ratio as much as possible. Why? Because all the information in this ratio was provided to you in the problem. What you want to try to stay away from, unless it's impossible, is to not use answers that you found because A, you rounded them, and B, what if you made a mistake? It's just going to make more errors throughout the problem. So what we do is we go back to 14 over the sine of 82, and this time we set it equal to B over sine B. So we don't know what b is, little b, but we now know that big B is 34, so we're going to do the sine of 34. So if we follow the same algebra logic, we're going to get b times the sine of 82 is equal to 14 times the sine of 34. We divide both sides by sine 82, and we get 14 sine of 34 over the sine of 82, which in the calculator is going to give you 7.9. So if you look at our results, we were provided with 3 pieces of the triangle. We had to find the remaining 1, 2, 3 pieces of the triangle, which are going to be the solutions to our problems. Well, I wish it would be the solution to all our problems, right? But the solution to this problem, I guess we'll go with. So in this scenario, that's essentially how you do a law over sines problem. Note, they don't always ask you to find all the remaining pieces. It might occur on an exam that I might give you just one of the missing pieces, but it depends on, what the exam is like. Okay, so let's try another one. Last one from this scenario that we're dealing with here in terms of practice problems. So again, we have a triangle ABC, and we're asked to find the missing pieces by law of sines. So it looks like the missing pieces are angle C, side A and B, right? That's what we're going to have to find for the sake of our problem. So the first thing we have to do to see if we can use the law of sines in this oblique triangle is to verify the pattern. So let's see what we're given. We're given 2 angles, and we're given the side. So if you look at it, it appears that the side here is between the 2 angles. So that produces a pattern of ASA. So again, what is it? It's a side that's between the 2 angles. So therefore, we pick the pattern ASA. You guys should be experts at this pattern stuff just because you did it so much in geometry long ago. It's going to be about bringing that knowledge back to you. So what do we do second in the problem up here? Well, we try to find a ratio of pieces that are opposite each other. So let's look at that. Look at A. So it looks like we have side A. We don't have, but we do have the angle opposite it. Okay, so that's not going to be it. If we look at the angle B, do we have the side opposite it? Again, we don't have that. If we look at side C and angle C, it appears we don't have angle C, but we do have the side opposite it. But just from the previous problem, you know that we can easily find C by doing 180 minus the sum of the other 2 angles. If we do that, we get 117.5 degrees. So, even though we had to do a tiny bit of work in the beginning, we now have an angle in the side opposite it. So again, our key values are going to be C over sine C, which is going to be 12 over the sine of 117.5. So we're likely going to be using this twice in order to find our missing pieces. So I'll put a cloud around it again. Okay, so what does that look like? Well, let's find missing pieces. So we're going to do 12 over the sine of 117.5. Why don't we go to A because it comes first in the alphabet. So what do we got here? It looks like we have little a over the sine of the angle opposite it, 40. Okay, so again, you'll see that this is set up exactly like the other problems. Therefore, all we have to do is cross multiply. Now, worth noting, we can really take a shortcut here. How do we know that? In the problems that we did, no matter what happened, we would always get this variable is equal to the product of this divided by this one. So we should be able to do that in all the other problems. So A is equal to the product of the diagonal, 12 sine of 40, divided by the one opposite the variable, which is a sine of 117.5. You could cross multiply if that's easier, but this is a nice shortcut to make life easier for you. We're going to get 8.7 when we do the work in the calculator. So that's our first missing side. We want to do the same thing for B this time. So we got this is equal to, it looks like the missing variable is B. and then the angle opposite it is 22.5. So again, the variable is going to be equal to the product of the opposite diagonal over this angle trig function opposite the b. Wrong place for that point. So that's going to be equal to 5.2, which means already we have found all the missing pieces to the problem. Okay, so some semesters I do cover this, but because of the insanity with what's going on in the world, I decided not to, just because there's a lot involved with it. So there is another, I'm going to read it actually, just so that you can get a good view of what it's about. It says, it turns out that if you have two sides and the angle not between them, so for example, let's try this. So let's say we're given 5, 7, and the angle not between them. So let's say 36 degrees. Okay, so side and the angle not between them. This is actually referred to as SSA. If you reverse the letters, then of course you get an even funnier term. But SSA is what they call it to stay away from the people laughing about it. But the key is that you can actually also utilize law of sines in this scenario, but it creates a very complicated situation called the ambiguous case. Why is that? Because it turns out that when you're given a scenario like this, the pattern doesn't create a unique triangle. It actually creates different scenarios of triangles, which means when you're doing a problem like this, you would actually end up with two sets of answers. Hence why I think I'm going to stay away from that this semester. But worth noting, law of sines can be used on this pattern. It's just that for the sake of what we're doing, we are not going to be covering that pattern in terms of class and in terms of what we're going to be doing. So instead, let's move on and talk about some word problems with the law of sines. Number 3, it says the Leaning Tower of Pisa in Italy leans at an angle of 84.7 degrees. The figure below shows 171 feet from the base of the tower. The angle of elevation to the top is 50 degrees. Find the height of the tower B. Okay, so obviously with a leaning tower, we are not dealing with a right triangle. So this is an excellent application problem where you would have to look at this immediately and say, hey, this is not a right triangle, this is an oblique triangle, which means I got to get on determining the pattern of our problem. So let's look at what we're given. We're given two angles, and either the side away from them or the side between them. Well, you can clearly see that the side is between the two angles. In other words, the angles are actually shared by that side. So therefore, the pattern is ASA. Once you determine that this pattern is okay in terms of what it is, you now are able to use the law of sines in order to figure out this problem. Now note, what are we trying to find? We're trying to find the length of this side. So how do we do that? Well, if you look at the problem, what would we do? We would again try to find a side and an angle that are both given that are opposite each other. Well, if you look at B, we're clearly looking for that, so it's not going to be that. If you look at A, you can see 84.7 degrees is the angle, but the side, I have no idea what that is. So again, if you look at 171 feet, we are given that side. Even though the angle is not sitting right here where it is, we obviously can do 180 minus 84.7 times plus 50 and get 45.3 degrees as the missing angle. Now, that is not the angle that the problem asked for, but we need it in order to solve the problem. So what are we doing? Well, we now have a ratio of C over sine C, which is essentially 171 over the sine of 45.3. So we need to now set that equal to a ratio including B, because that's what we're trying to find. So it's going to be B over the sine of the angle opposite it, which is 50. If we solve that, we're going to get B is equal to diagonal product of the opposite diagonal divided by the sine evaluation that is opposite to B. We are going to get in our calculations approximately 184.3 feet for the height of the tower. So this is a very straightforward problem. I like it because I tend to like the problems where it just asks for one thing as opposed to everything, but that's only because it's not repetitive law of sines, it's just straightforward and to the point. All right, number 4, it says triangulation can be used to find the location of an object by measuring the angles to the object from the 2 points at the end of the baseline. It says 2 lookouts 20 miles apart, so we got lookout A and lookout B that are a full 20 miles apart from each other. Both of them basically spot a ship at sea. So both of these guys are looking in this direction, right? And they see this ship somewhere at sea. Use the figure below to find the distance d of the ship from the shore. Okay, so basically our goal is to find this variable d. Now this is a very interesting problem because if you look very closely at what's going on here, we basically have a missing d that's in either one of the right triangles that you see. In those right triangles, you are provided an angle in each one, but you are not provided a side. So when you look at the piece over here or over here, we're not given that. You're also only given the full length from A to B, which is 20. So again, here and here, you're not given that. So that provides a very interesting situation where we have to figure out how we're going to find those missing pieces. So first of all, we can't use right triangle trig right now because we have if we want to use, let's say, this triangle, we don't have any missing pieces to use. So right triangle trig is essentially out the door. So what we want to do is we want to look at the big triangle. If we look at the big triangle, we already know that it's this one here, big triangle. We know likely that it's oblique. We know that angles are 49 and 38, and we can find this angle, 180 minus 49 plus 38, which is going to give you 93 degrees. So if we redraw this picture with a 93-degree angle, a 49 and a 38, and a 20 on this side, you should see basically that if we just ignore this for a second here, we're given 2 angles and the side between them, which is ASA, which means we should be able to use the law of sines in order to do this problem. So we got our 93 in the scope of the problem. We look at it and say, well, do we have any angles and sides opposite? We do. We have a 93-degree angle opposite a 20. So we should have a law of sines ratio of 20 over the sine of 93. Okay, if we do that, we basically just have to choose which one of these sides we want. It actually doesn't matter which side we pick, and I'll show you that later. I'm just going to choose the one on the, let's just do the one on the left. So if we set up that ratio, it's going to be, let's call it x. Okay, we'll call this x. Yikes, that's an asterisk, not an x. So we'll call that x. So we're going to do x over the sine of the angle opposite it, which is 38 degrees. So if we solve this, we're going to get x is equal to 20 sine 38 over the sine of 93, which is going to give us 12.3 as the missing side. So I'm going to write it in the picture. This is going to be 12.3. So this is essentially step 1. Once we get that missing side, something very nice happened. Watch. So look at this right triangle we have right here. We actually now have an angle, 49, and a side, 12.3. So we should be able to easily find the missing piece of this figure, which is D. Okay, how do we do that? Well, we have our angle in a right triangle. We are trying to find the opposite, and we're given the hypotenuse, so that is essentially sine. So the sine of 49 is equal to D over 12.3. So just to be clear, this is not the law of sines. This is just trig 101. of setting up a ratio. So how do we do that? We multiply both sides by 12.3. So we get 12.3 times the sine of 49, and we're going to get approximately 9.3 miles as the result for our problem, which is going to be our answer. So this is very unique in the sense that this was a two-step problem, and you were able to use basic trig, in order to figure it out as well, but we needed the law of sines in the beginning to get there.